As we start the second movie on this topic, you'll have noticed that I've broken out the various blocks. So I've pulled the S block over to the left of the D block, removed it a bit, and removed the P block to the right of the D block. And this just enables us to see a little bit better what the subshell numbers are in each block. And before we get into the more complicated stuff, I always find it's really useful to practice understanding the periodic table just in terms of looking at the position on the periodic table of different atoms, different elements, in terms of which block, which subshell in the block, and where they are in that particular subshell. So let's illustrate this with 4 examples, starting off with lithium. Right there. So first of all, what block is lithium in? It's in, I hope you will see, the S block. Okay, so anytime we talk about the S block elements, we're including lithium and all its friends. Now the S block consists of 7 subshells. 1s, 2s, 3s, 4s, 5s, 6s, and 7s. Which subshell is lithium in? Well, it's in the 2s. Now within the 2s subshell, there are 2 different elements, lithium and beryllium. Lithium is the first, beryllium is the second, and so we'll illustrate that by saying lithium is the first by saying 2s1. Let's do phosphorus next. What block is phosphorus in? Well, it is in the P block. Now the P block in our current version of the periodic table has got 6 subshells, starting at the 2p going down to the 7p. Which one is phosphorus in? It is in the 3p. Within any P subshell there are 6 elements. Okay, which one is phosphorus in terms of in the 3p? Well, aluminium would be the first, the silicon the second, phosphorus thus the third. So phosphorus is 3p3. So move on to technetium, fascinating element, one you will learn about a lot when you get into the bioinorganic module in the 3rd year of the fundamental course. So technetium there, which block is it in? Well, it's obviously in the D block. The D block has 4 subshells. It starts at 3. So 3D, 4D, 5D, 6D. One of the harder things for people to remember at the start is that the D starts at 3. Even though it's sandwiched between the 4S and the 4P, the D starts at 3D. Well, we're not in the first D subshell, we're in the second D subshell, which is in the 4D. Now, within any D subshell, there are 10 elements. Which element are we in terms of technetium? Well, it's the 1, 2, 3, 4, 5th one. So technetium 4d5. Finally, hope it's no great shock to you if we exemplify one from the F block, ES, Einsteinium, named after the dog in Back to the Future. I'm just kidding. The dog and the element named after Albert Einstein, but I like those movies, so I always want to refer to them. Anyway, the F block starts at 4F, even though it kind of starts here in a weird place after the 6S and one of the 5D and before the 6P, it starts at 4F. Now, Einsteinium is not in the first F subshell, it's in the second F subshell, thus Einsteinium is 5F. Within any F subshell, there are 14 elements. Which one is Einsteinian? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Einsteinium, 5F10. There's some practice on these in the quizzes. I'd like you to do that practice. Make sure you're really happy with our block breakdown of the periodic table. Make sure that you're happy with in each block, the subshells. In particular, notice the starting point. S starts at 1, P starts at 2, D starts at 3, F starts at 4. And if you can get really happy with this breakdown, it will help you not only as we continue in this course, moving into a more complicated application of this idea, but it will really help when you get into your next year, the first year of the fundamental degree. So hopefully, when you've got that sorted out, we can now go to our real electron configurations. Now cast your mind back to the shell electron configurations from the previous movie. What we were doing was we were saying we got these shells with these many electrons in them. Okay, so first shell, second shell, third shell, and so on. Now, of course, our model is more complicated than shells. It includes subshells. So now instead of just saying how many electrons are in each shell, we got to say how many electrons are in each subshell. And we can use our model for the periodic table to help us count through. Okay, so I want you to be sure you can see my little red dot as we go through it. Right, here's my little red dot. So let's start off with hydrogen. Hydrogen is nice and easy. Hydrogen has one electron. Where is that one electron? Well, it's going to be in the 1s1. So fairly trivial. Okay, how about helium? Helium's got 2 electrons. Well, let's count those 2 electrons. 1 electron in the 1s, 2 electrons still in the 1s. So therefore, both of helium's electrons are going to be in the 1s. Let's go down to lithium. Here, 3 electrons. Well, first electron in the 1s, second electron in the 1s, so that's 1s2, third electron in the 2s. So lithium, 1s2, 2s1. Beryllium, we've got 1, 2 in the 1s, 3, 4 in the 2s, so 1s2, 2s2. Moving over to boron, 5 electrons. So 1, 2 in the 1s, 3, 4 in the 2s, 5 in the 2p. Okay, so 2 in the 1s, 2 in the 2s, 1 in the 2p to get to 1s2, 2s2, 2p1. Okay, you don't need to use the brackets like we use for the shell electron configurations because you're just using the straightforward shell number, subshell number, number of electrons in there. Carbon, 1s2, 2s2, 2p2. Nitrogen, 1s2, 2s2, 2p1, 2, 3. And then just to finish off this particular row, get up to neon, which was 10 electrons, 1s, so that's 1s2, 2 in the 2s, and then 1, 2, 3, 4, 5, 6 in the 2p. Okay, so I hope you can see and start to understand how we can use the periodic table to build up those real electron configurations. Before we go further, we need to introduce a concept, an extension of what we're talking about, that because we're dealing at this at such a superficial level, you're just going to have to take my word for where all these funny things come from. Later on and again in the course, you'll be able to actually generate some of the things that we're talking about here. Anyway, when we were talking about our electrons in just a simple shell model, we knew where the electrons were. We knew where the orbit was. We knew that n equals 1, that electrons in that n equals 1 orbit. N equals 2, the electrons in that n equals 2 orbit. Now, of course, we've gone past the orbit model, past the shell model, into the subshell model. And so to go a little bit further, we have to introduce the concept of orbitals, which are now talking about where an electron is probably to be found. Something, again, we will go into detail next year. We cannot say where an electron's going to be. In the simple model, we said, hey, the electron's in this orbit, or it is in this orbit. Now we get to the point where we can't say where it's definitely going to be. We can just talk about where it is probably going to be. And each of the different subshells corresponds to a different volume of space associated with a particular electron. Okay, so an s subshell, for example, contains s orbitals, just one s orbital in each s subshell, and that orbital is a spherical shape. And the way we're going to depict that is a little box, and I'm doing it as a red box because I'm calling my s subshell and my s orbital red. You get up to a p subshell, and there are 3 possible orbitals in a p subshell. Okay, 3 volumes of space that have the same energy for the electron, and we call them all folded up into a p subshell. Now the shape of a p orbital, and remember all an orbital is a volume of space in which an electron is probably to be found. The shape of a p orbital is often described as a dumbbell shaped, or a kind of weird figure of 8 shape, or even an infinity sign shape. Okay, and so there are 3 possible p orbitals in a p subshell, because you can have a dumbbell that goes along the x-axis, you can have a dumbbell that goes along the y-axis, and you can have a dumbbell that goes along the z-axis that's going in and out, and this is just rotation there to show you that dumbbell along the z-axis. Px, py, pz, the 3 orientations of the p dumbbells in a given p subshell. And we will depict these in a minute with 3 little green boxes, all on the same level, because it doesn't actually matter which of these orbitals we choose, which orientation we choose. They're identical in size, they're identical in shape, they're identical in energy. The only thing different with them is their orientation. Get up to the D subshell. There's 5 orbitals in a D subshell, and they have these shapes here. Pretty much the default shape is this sort of 4-leaf clover. So you've got 3 4-leaf clovers that are kind of between the axes. So this one's called the DXZ because it lies on the XZ plane. This one is the DXY, lies in the XY plane. This one, the DYZ, it lies in the YZ plane. This one here is still a 4-leaf clover. It's actually on the axes now. And don't worry about where this one comes from now, this 5th one that we call the DZ squared, because it's pretty much just going up and down the Z axis. It's like a dumbbell with a little belt. Don't worry too much about that shape. Just recognize it as being a indicative shape of a d orbital. 5 d orbitals, they all have the same energy. They just have different shapes and different orientations. And so the way we'll depict those is 5 little blue boxes. Now, for the sake of completeness, I'm going to mention that the F subshell has 7 F orbitals. I'm not even going to think about drawing those. There's a link there that you can use to go have a look at them. And because we're not going to be getting so complicated as to talk about F subshells and F orbitals, I'm not even going to draw boxes, but of course there would be 7 orange boxes. So now, using the ideas of shells being split into subshells and subshells being split into orbitals according to specific rules, we can now go ahead and finish off over the next 3 or 4 slides the whole electron configuration conversation here. Okay, remind you of the Aufbau principle. Electrons go into the lowest energy available orbital. Okay, orbitals being in subshells, subshells being in shells. Okay, so a hydrogen 1s1. The way we're going to draw this is an electron in that 1s box. So it's 1 electron in the 1s subshell, and that 1s subshell has 1 orbital, a nice little sphere in which that electron is probably to be found. Helium 1s2. Okay, first electron goes in the 1s. We said the second electron also goes into the 1s. Helium's 1s2. But the way we draw it is, instead of it being an up arrow, it's a down arrow. Okay, now this is concept of spin. Effectively, we can think of this electron spinning one way, this electron spinning another way, and we utilize the so-called Pauli electron exclusion principle, which says no more than 2 electrons in an orbital. A fancier way to say that is you can't have more than 2 electrons in the orbital, because you've either got one spinning one way, the other spinning the other way. You can't have 2 electrons in the same orbital spinning in the same direction. Again, we'll worry more about that next year. For now, just take it as the Pauli exclusion principle. No more than 2 electrons in an orbital. Move on. Lithium, easy. 1s2, 2s2, 2s1. So there's the 1s little box, and there's the 2s little box with 1 electron in there. Beryllium, 1s2, 2s2. Just going to be like that. 2 electrons, 1 up, 1 down in each of the 1s and the 2s boxes. Next fun bit comes when we get the boron. 1s2, 2s2, 2p1. Well, there's the 1s2, 2s2. 2p has got 3 boxes, remember that, and let's put that 1 electron in there. So now 2 electrons in the 1s, 1 up, 1 down, 2 in the 2s, 1 up, 1 down, 1 in the 2p, in this case drawing it going up. There wouldn't have been anything wrong with drawing it going down, it's just an electron in the 2p. Now where that does become important is where we move to carbon. 1s2, 2s2, 2p2. Well, we know that 2 electrons in the 1s, 2 in the 2s, and here's the 1 electron in the 2p. Now we've got to stick another electron in the 2p. And now we have a choice. This is actually the first time we've had a choice. Okay, is it going to go there? In which case it would have to point down. Is it going to go there, pointing up, pointing down, or there, pointing up, pointing down? Now, of course, these two are essentially the same because they don't have an electron in there. But the question is that electron, that 6th electron, the second one we're going to put in the 2p, is it going to go into the orbital that already has 1 electron in it, in which case it has to go down, or is it going to go in one of the 2 empty orbitals? And if it goes in one of the 2 empty orbitals, does it point up to match the one that's already there? Does it point down? This is where we have to learn about Hund's rule. This is actually one of 2 of Hund's rules, but we only worry about one of them now. And Hunt said that electrons will enter an empty orbital rather than a half-filled one of the same energy. So in other words, it's going to go either here or here. It's not going to go in the one that's already got an electron in it, and it enters with a parallel spin. So I'm going to put it in pointing up. Nitrogen, where's that 3rd p electron going to go? Well, according to Hund's rule, it's going to go in that one empty one right there. Now at this point we have a half-filled p shell. We've got each orbital has 1 electron in it, and I want you to remember this half-filled p subshell concept in a later movie. Okay, there's something nice and special about a half-filled p subshell. Oxygen got another p electron. Well, now that's got to go in one of the ones that already has an electron in it, a half-filled one, but now going back to the Pauli exclusion principle, is going to go in with its arrow down because there was already one in there with the arrow up. Fluorine, a 5th electron goes in with its arrow down, and then neon finally 1s2, 2s2, 2p6. You've got the 1s is filled, the 2s is filled, and now the 2p is filled with those 6 electrons. And again, remember what that looks like. That is a filled p subshell, and as we will see later on, something very, very, very special about a filled p subshell.